Hi, good morning, and welcome to the lesson on relative velocity distance time graphs. Basically, by the end of today, we're going to be able to describe what a distance time graph is. And if it were at school, you'd probably be drawing one, but you're not, so you don't have to. Lucky you. But let's start just by reviewing some of the important things that we had reviewed in the previous lesson. So speed, distance, time, all linked together in an equation. Can you write out the equation 3 times with speed as the subject? Speed is equal to, and then distance is equal to, and then time is equal to. Then can you do the equation for acceleration? And then the last part, what is the difference between speed and velocity? Well, pause the video, answer the questions, unpause when you're done. Check. Okay, so let's just review. There's the pen on. It is, right, write the speed, distance, time equation. So if I do it like this in the triangle, we can write speed is equal to distance divided by time. Time is equal to distance divided by speed, and distance is equal to speed times time. Acceleration is A is equal to change in velocity all over time. And the last one, the difference between speed and velocity. Well, they're both measured in meters per second, so that's a similarity, but the difference is one has direction and the other one doesn't. So speed is directionless. It doesn't matter which direction you're going with. Velocity, the direction is very important. It matters what you're going. So velocity is like speed, but with direction. Okay, so this is a good example of actually the difference between velocity and speed. These two cars are traveling at the same speed. You can see the speedo. This one says 40, and this one says 40. But you notice they're going in different directions. So they have different velocities. In fact, you might say one has a velocity of 40 miles an hour, and the other one has a velocity of minus 40. Sometimes the minus tells you the direction. Or you could say one 40 miles an hour east, the other 40 miles an hour west. So same speed, different velocities. So another way to look at it. And actually, this leads us on to the first part, which is about relative velocity. And relative velocity, well, what is this person doing here? First guy, you might think he's going to shoot you, but no, he's not. He's not holding, it is a type of gun, but it's a radar gun. And do you know what it's designed to do? Yes, it's designed to determine how fast something is going. It sends out a little radar microwave signal that bounces off a car and comes back, and it can work out how fast that car is going. But that will only work if this police officer or whoever's holding him is not moving. If he's moving, it will give you a completely different speed. What he'll give you, what he's measuring there, is your relative velocity. And the relative velocity is how fast is this car going in relation to me? And he's going 0. He's not moving at all. It's another slightly more extreme way of thinking it. If you've ever been on a train, not like a tube train, but whatever, and you stare out the window, you'll see houses going by. Zoom, zoom. Are the houses moving? Has your house ever moved? No, it doesn't. But relative to the train, it's moving. So the house is going past at 80 miles an hour. Actually, you're going past the houses at 80 miles an hour, but depending on where you're looking, because when you're sitting in your seat is moving with you. So the seat and the train are moving at the same speed, and the window is moving at the same speed. So actually, it looks like you're still, everything else is moving past. Relative velocity is how fast is something moving in relation to something else. And if you carry on studying physics up to A level or degree level, you get to do things like relativity, where it comes up with some crazy answers. But relative velocity is all about comparing speeds, and speeds seem very different if one thing's moving and another thing's moving in a different way. Actually, if you've ever sat on a train and it's pulled out of the station and you're next to, like, there's a train next to you, and the train pulls out, or you pull out, actually, it's not easy to tell who's moving and who's not. Sometimes the train moves off and you think, oh, that train's going, and then you realize it was your train. It's all kind of relative, how fast something's moving in relation to something else. If we look at this example, so if you were on that train going at 80 miles an hour, you would see that car going past at 70 miles an hour, but it wouldn't go at 70 miles. For you, it would be going at 10 miles an hour slower than you. So the train, and the car, what would happen is if they start at the same point, the train would just move off slowly in relation to the car. Actually, if you're in the car looking at the train, you'd see the train go like forward, whereas if you're the train looking at the car, you'd see the car go backwards because the car is going slower than the train. Relative difference, 10 miles an hour. But if you're on that train and you look at the yellow car, this train's going 80 miles an hour that way, that car's going 70 miles an hour that way. That's actually a difference of 150 miles an hour. So if you're on that train and you see that yellow car, you'll see them moving so fast. So despite the fact that those two cars are traveling at the same speed, they have opposite velocities. One is 70 miles an hour, one minus 70. They're going in opposite direction. And so according to the people on the train, the yellow car, is going incredibly fast in that direction. And the black car is going really slowly, and it's just disappearing behind. So relative velocity is all about how you're going, how fast you're moving. And relative velocity can have some really crazy notions. There's a little GIF on the next page, but if you watch this video, this is a slightly longer version. So if we look at the image on the right, this one, so what's happened is these individuals, this is a Myths Plus episode where they've created a kind of cannon that fires a football out at 40 miles an hour. So that if the car was still, you fire out and you'll see the football fire out at 40 miles an hour. But they're driving the car at 40 miles an hour. So the car's driving, the car is going this way at 40 mph. It fires the football out this way at 40 mph. So the car's going one way, football's going the other way, and so when they fire it obviously in front of this kind of checkered pattern to make it visible. You see that the relative velocity, 40 miles an hour one way and 40 miles an hour that way, actually the relative velocity cancels out, so the ball just drops down. The ball is actually moving 40 miles an hour in that way, but because the car was fired, it looks like it's dropped right down. So if you fire a 40 mile an hour ball one way from a car moving 40 miles an hour the other way, you look at it from our position, it looks like it dropped. But if you watch the video and you look at it from the car's point of view or the truck's point of view, you can definitely see the ball moving. It's all about relative velocity. This one as well, it's the same thing. You see these guys on the trampoline, they're flicking this guy being dragged by a tractor. I actually don't know what this is from, but it's the same principle. Like normally, if somebody pulls a trampoline out from underneath you, the trampoline will move and you'll fall down. But because all of these people were moving on the trampoline at the same time, so they're moving with the trampoline, when they bounce, they're moving at the same velocity as the trampoline, so they don't disappear underneath it. What's happening, the relative velocity means that this person is moving, the person on the trampoline is moving at, say, 20 miles an hour, the same speed as the truck, the tractor, the same speed as the trampoline. So it just looks, in relation to the people on the trampoline, that he's just moving up and down, but he's moving up and down and traveling right at 40 miles an hour or 20 miles an hour. It's all about where you base your perception from. Where do you look from is where you can take your relative velocity. If you're moving with a truck, it doesn't look like you're moving. When you're sitting on a train and you look at everyone around you, you don't look at the person next to you going, well, he's going at 80 miles an hour. Of course you don't, because you're moving at 80 miles an hour with him. So relative to you, that person's not moving. But relative to somebody outside, that person really is moving quite fast. Perhaps it's easier to draw some of this in a diagram. So you're going to need to draw these down, copy this down. So the first thing with a pencil and a ruler is copy down that axis, distance time graph, an axis, an x-axis, and a y-axis. Go. What do you want? Okay, so distance time graph and axes. So we have the x-axis and we have the y-axis. The y-axis is equal to the distance. And the x-axis is equal to the time. Always, time is always on the x-axis. We can't control the time in this situation, so we put it on the x-axis. Here we go. So you add these. Where they meet is 0. This is our reference point. This is our starting point. So 0 is the axis. So add these labels to your diagram. Pause. Add these labels. You're going to add more in a minute. Okay. So let's look at this line. What does this line tell us? This line tells us, well, how would you describe this line? First of all, this line, horizontal line, okay? Horizontal line. So what's its gradient? 0. It has a 0 gradient. So it's traveling. So this thing at time 0 here, it's at, I don't know, say what that is, 5 meters. Yeah? At time later, it's still at that same distance, 5 meters. At another time, 10 minutes later, it's still at 5 meters. Look, as time moves along, this thing's distance does not change. So what does that mean? A horizontal line, a straight horizontal line means this is not changing. This is a stationary object. On a distance time graph, horizontal line means that the object is stationary. At 0 seconds is 5 meters. At this time it's 5 meters. At this time it's 5 meters. At this time it's 5 meters. All throughout time, this object is still at 5 meters, which means it's classed as stationary. Add that down. Write that down. Add it to your graph. Go. Check. Now, this is different. Obviously, this is not the same. This line is increasing. So we notice at 0 time, the object has not moved. If you move a little bit further along, the object has moved along a distance. If you move it, time moves further along, it's moved again. Actually, you see this distance here and this distance here, if they're the same, this distance here and this distance here are the same. Which means if you have a straight line, a straight but diagonal line, it means the object is traveling at a steady speed. A diagonal line, an increasing line, means the object is traveling at a steady speed. Another thing to add to your graph. You got that? If not, pause it. Difference between these two lines, okay? So this one takes half the amount of time to go the whole distance, whereas this one only does half the distance in all of the time. So this line here, in small amount of time, goes a long way. This one means it's going fast. So if you have a diagonal line, but with a steep gradient, it's going fast. This one here takes a long time and it doesn't get anywhere near as far as the other one. A shallower gradient means it's moving slower. Steep slope, fast. Gentle slope, slow. Two more things to add to your graph. Huh? Excellent. So, look at this for a second. What's happening? This section here, this person was, we know this means they're moving at a steady speed. Steady speed, steady speed, steady speed. And then they stop moving. Why would the graph go by that down? We'd only kind of tricked you on this one. This is a slightly different one. I've changed this to displacement. Sometimes when the graph goes back down, that person has gone back to their starting point. So it's like they've gone doo, 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 doo. So they've moved at a constant speed, they've stopped and gone back. It's like you walk out the house, you get to the end of halfway road, you realise, I've got my phone, check your pockets. Damn, right, go back. That's basically what that is. Someone's gone somewhere, trying to remember whether they've got something, and headed back again at the same speed. Straight line, horizontal straight line, not moving. Straight line diagonal, moving at a steady speed. If it's going down, means we have a velocity, means it's going backwards. Ooh, look at this one, slightly different. Smoother graph, smoother curve. Distance time graph for a car. So we talked about if you have different gradients, you have different speeds. So if we look at the start, gradient, 0, car's not moving. Look at the end, 0, car's not moving. So it starts, so it's not moving at the start, and it's not moving at the end. In between, we have this horizontal, it's not horizontal, this straight line, so it's moving at steady speed. But between that, the line is changing. As the line changes, that means it's going from 0, and then the speed's increasing. This shows the curve, shows the car, like upward curve, shows the car is accelerating. It means it's getting faster. So it goes from 0, and anything above 0 is getting faster, and then it's increasing, and then it gets to a constant speed. So, for example, pulling out from the lights, slow, starts increasing speed, going at constant speed. Oh, next set of lights up ahead, brakes, slows down, comes to a stop. So where the line goes from being diagonal down towards a horizontal, slowing down, deceleration. The car is decelerating. And then at the end, that means we have no change. Horizontal, the car has stopped moving. So a very good example, like say you're stop testing traffic lights, the lights go green, press the accelerator, the car starts moving more slowly at first, and then as it gets up to 20 miles an hour, if we're in a built-up zone, going at 20 miles an hour for a period of time, and then you see another set of lights, they start to change, you press the brake, the car slows down, then you come to a stop, so the graph is horizontal. You can actually use the graph to work out the speed. If the graph is distance time graph, you're working out the speed. If it's a displacement time graph, you'll actually work out the velocity. And it's all linked to that gradient. The speed of a car can be calculated by looking at the distance time graph. It is, obviously, we know that the distance divided by time is a speed, which is the same as the change in y over change in x. The gradient of a distance time graph, will give you the speed. The gradient of a displacement time graph will give you the velocity. With a distance time graph, the speed's always going to be positive. That's because it doesn't have direction. With a displacement time graph, the velocity can be positive, or it can be negative. So there we go, straight line in the middle. It's traveling 600 meters, and it does it in a time of 20 seconds. So 600 divided by 20, 30 meters per second. Do you remember how fast that was in miles an hour? Roughly double it, about 60 miles an hour. It's pretty fast, so it's kind of some dual carriageway. Now it's your time to answer some questions. My head's in the way. This picture shows a distance time graph for a woman who went for a run in the park. The sections of her journey are labeled A to E. I didn't follow this woman, it's just a made-up question. Here we have A, B, C, D, E, different sections on the graph. Time is on the x-axis, this is time in minutes. Distance is on the y-axis, distance is in meters. You just have to choose which part of the graph was the woman not moving. A, B, C, D, E. Which section was the woman going the slowest? Again, A, B, C, D, E. Describe the section of the journey. Describe section of journey D, including the distance traveled and the time taken. 4, can you just describe what was happening? I mentioned before, like, someone moving at constant speed, they stop, check their pockets. Oh, they decide they've got something, they go back the other way. Can you do a similar thing for this person's journey? You don't have to come up with ideas why, just what they're doing. And then in section B, can you calculate the speed of the woman traveling? And the last one, different axes. Look at this one. This axis is displacement, not distance. So we're looking at a velocity, time, seconds. The displacement time graph for the motion of a boy doing the bleep test to check his fitness. He runs backwards and forwards between two cones, starting at one of the cones. Calculate the boy's speed. For the graph shown, one of the cones has been chosen as a position of 0. Redraw the graph so that it still shows the boy's motion, but with 0 halfway through. And it says redraw, just sketch. Now, that's it. Wow, easy. Hope you do well. Love you. Bye.